Okay, so I think we can start this session now. So, good evening, everyone, and welcome to the week 10 live session of this NPTEL course entitled Machine Learning and Deep Learning Fundamentals and Application. So, in this particular live session, we'll solve the week 9 quiz. In week 9, we have seen some of the techniques related to clustering, and we have already seen that clustering is a means of grouping the data, and there are several sort of clustering techniques that we have seen in the earlier week lectures as well. So to say, in week 8 we have seen the uh, Markov model based Gaussian mixture model based clustering techniques, which basically fits different weighted sum of Gaussian probability density functions to capture the hidden patterns inside the data, or so to say the clusters of the data. Then after that, we have also seen that how we can employ k-means clustering method. So in case of k-means clustering method, we have solved a very rigorous numerical problem as well in the last week, which basically dealt with several sort of data points were there, and they have also initialized with some centroid, predefined centroids, and using that iteratively, so we went for 3 iterations and we saw that the convergence is already that time it had been reached. So therefore, for that particular case as well, we had seen that how to go for an iterative method to do the clustering process. Now, in this particular week, we have seen that there were mainly 2 topics. One was in the last week, we have seen the strict uh, k-means clustering. In this particular week, we first started with the fuzzy k-means clustering. So in case of strict k-means clustering or the standard k-mean clustering, you had seen that the data point at the inference time, the data point can belong to a particular data group. So therefore, the decision whether the data belongs to group 1 or group 2 or group 3, or so to say for group n. So the decision is quite hard decision. However, in case of fuzzy, in any fuzzy techniques, you will see that the decisions are not hard, rather they are soft decision and based on some sort of a probabilistic measure. So the probabilistic measure basically helps you to accommodate that whether the data has some sort of an uncertainty, that the data might belong to class A as well as it might belong to class B or class C, something like that. So it contains the probability of uncertainty in the decision making process than the standard method where the decision is quite hard decision. So you have either zero state or one state in case of standard method, but in case of uh, what you call the fuzzy clustering method, you will see that uh, it gives you a wide regime of probabilistic measure. For example, if you say probability is 0.9 for belonging to a data group, uh, let's say probability 0.7 for belongingness of a data to cluster 1. So that means it has a 70% chance that it belongs to cluster 1, and rest of the 30% there is some sort of an uncertainty. It may belong to class B, class C, something like that. But in case of standard uh, k-means clustering, that provision was not there. It was a quite hard decision. Either it may belong to, let's say, class A, otherwise you cannot uh, actually make any decision about that. So it is like a one hot uh, decision. And in the next segment, we have seen the other variants of clustering method. For example, HSE clustering, that is hierarchical uh, agglomerate clustering. So in that case also we have seen that uh, we have, if we have a pool of data, so what we do over there, we declare each of the data point as the cluster, and then iteratively we try to see that which of the data points have a smaller distance metric or smaller similarity or higher similarity metric. So we club them together, and in this way, again, iteratively, we reach the convergence, and we can see that this sort of some sort of a clusters have been produced. So in majority of the cases, as because this is a theoretical course and we have to show some numerical problems, so you can understand that we have to give some problems which are tractable numerically, but largely you'll be basically applying these methods on a wide pool of data, not just like in the quiz question. You can see that they give you a data pool like seven samples or eight samples. You will basically not employing these methods on seven or eight batch of data. Rather than that, you will be basically employing on large scale of data. Eventually, you've seen in the week 2 live session that I dealt with some of the standard data sets that is there in PyTorch as well as TensorFlow. So in case of PyTorch and TensorFlow dataset, one second. So in case of PyTorch and TensorFlow dataset, you're seeing that we dealt with Cypher10 dataset, which had images of different objects such as uh, car, bus, ship, frog, etc. There were 10 classes. Similarly, we have seen the MNIST digit dataset, which basically comprises the handwritten digit starting from digit 0 to digit 9. So in both the dataset, we can see that the dataset is not quite imbalanced dataset, or therefore there is no skewness in the data, but we have fairly large amount of data there. In the training set, in both of the cases, merely we had a data pool of 50,000 data in the training set and 10,000 data in the testing set. So you can understand that majority of the methods that you are seeing in the course, practically you will be implementing on a wide pool of data, not just as two, 8 or 10 cardinality that you can see in the question. So I would also recommend you to do some sort of coding practice as well, so that you can understand the concepts well. Probably in next or in next week, I will be showing you some coding demonstration, because now we are reaching towards the deep learning part, and deep learning part, as per me, it should be it should have some sort of a hands-on uh, uh, ex explanations too. So therefore, in the next week, I will simulate some of the neural networks in the in uh, Python as well. So let us now start solving the quiz. So as because in this particular week we are mainly focusing on clustering based methods. So the think I have some issue with the pen. One second. Okay, fine. So the first question states that which of the following statement is true for HSC with complete linkage? So there are different sort of linkages that you'll see. For example, single linkage. So these linkage basically means the distance metric. So these are, for example, linkage, complete linkage. These basically refers to the distance metric used in the hierarchical agglomerative clustering method. So any of the clustering method that you have seen, so all of this clustering method basically deals with some sort of a distance metric. So in the last class, we have seen that Euclidean distance. In this particular class, you can see that single linkage, complete linkage. So different methods basically introduces different sort of distance metric, because anyway, you can understand the clustering methods are unsupervised methods. So therefore, you do not have the labels corresponding to the data, because this is an unsupervised method, so you'll not have the labels of the data. So what you are effectively trying to do is basically you're trying to find the data, or you're trying to group the data based on their similarity. For example, if you have a bunch of only pens are given. You know that if you have given a kid a lots of pen, you have given to him. So now as per the human tendency, or by human very nature, we can see if you've been given something and if you do not know anything about something, what we do, we try to group things together. So for example, if you have a lot of pens, then what you will do, you'll try to group them. Now, based on what criteria you will basically group them? So there is no such uh, mm, unique way to define that how you'll be basically grouping them. So one way of grouping could be based on the length of the pens. Another way of grouping the pens would be the color of the ink of the pen. So based on that, Based on that, you can put red pens together, black pens together, blue pens together, like that. Again, you can also club them together based on their property, like whether this is a ball pen, whether this is a gel pen. So therefore, you can understand that there is no certain unique method by which you can loop them together. So there could be n number of possible scenarios, and these possible scenarios basically, in the practical case, in the algorithmic case, these are basically the distance metrics. You can impose any sort of distance metric to do the clustering process. So in this particular case, in the HSC method, there are different sort of linkages they have introduced. One could be single linkage, one could be complete linkage. There are several other notations are also there that you can see in the original papers as well. Okay, so far the question is being concerned, which of the following statement is true about HSC with complete linkage? So the correct statement about HSC with complete linkage is basically, we know that in case of complete linkage, so let me just write it. In case of complete linkage, so what we basically mean by complete linkage? So if we try, if we just get to know about what is complete linkage, that is the basically answer of this particular question. So complete linkage is basically defined as the maximum distance between any pair of points one from each cluster. So what does this particular line means? So let me just show you a visualization. So let's say you have two clusters. So let's say this is a cluster one. Let's say a cluster of green pens. And then you have cluster two, which is basically a collection of red pens. Right? Now you are basically trying to calculate the distance measure between these two uh, cluster groups. And complete linkage basically means that, so let's say here, over here, you have j number of points. And in this particular group, you have I number of points. So you can calculate dij, and you're trying to find maximum of dij. And obviously, so you're basically trying to calculate the maximum of dij. So in this case, the complete linkage, the can be illustrated like this. So what you are doing, from this point, you are calculating distance. From this point, you are calculating the distance. From this point, you're calculating the distance. And you're trying to find that any of the data pair from this point, from this particular group. So this is a group and this is another group. From any of the groups, you choose a pair of point, you calculate the distance, so which will give you dij. So d is basically the functional representation of Euclidean distance. So given this, you take a point pair from both the groups, then you calculate the distance, which will give you dij. And from out of all the distance value that you have calculated from these two data groups, then you take maximum of that. So which is basically nothing but the uh, complete linkage of HSE method. So now let us try to see what basically the complete linkage in HSE tells us. It tends to produce elongate clusters. It produces spherical clusters. So there is no guarantee that it will create a spherical cluster because it is just a distance metric. It does not employ any sort of imposition on the shape of the clusters because that is invariant of the distance metric, because you're just calculating the distance between some point.
Hello? So you cannot hear you.
Then it tends to merge clusters within minimum distance between the centroids. It considers maximum distance between points of different clusters. So this is basically what the complete linkage means. It considers maximum distance between points in different clusters. So this is basically what the meaning basically suggests, this particular figure. So in this question, we have been given, let us consider we have cluster points P1 to P9. So therefore, the cardinality is 9. Cardinality of the data set is 9. And first, we take our K values as 3. So that means the K-means clustering basically says that you have 3 clusters to assume to begin with. We assume that the initial clusters have the centroids as P7, P9, and P8 as C1, C2, and C3. Then find out after iteration 1 what would be the new centroids. So to find that, what we have to do, so already I have told you that k-means clustering is an iterative process. So again, we have to see that how iteratively we can find that what would be the updated centroids. So therefore, what we have to do, we have to calculate the Euclidean distance from the point to the centroids. So in the current case, they have given that centroid 1 is basically point 7, which is 3 comma 3. Then you have centroid 1. Uh, so let me just write in a tabular fashion. So you have uh, points. So the points are P1 1 comma 3, P2 2 comma 2, P3 5 comma 8, P4 8 comma 5, P5 3 comma 9, P6 10 comma 7, P7 3 comma 3, P8 9 comma 4, P9 3 comma 7. So here I have annotated the data that have been given in the data set, and the initial clusters that have been given are cluster 1, which is 3 comma 3. Then you have cluster 2, which is 3 comma 7. Then you have cluster 3, which is 9 comma 4. So we know that we have to calculate the distance. We have to calculate the distance from the Pi to Cj, where I ranges from 1 to 9 and j ranges from 1 to 3. Because we have three centroids, as because the k value is 3. So to begin with, the iteration, we have uh, we have a preconceived notion that we have three sets of clusters, and given in the data set we have 9 data in total. So therefore I ranges from 1 to 9 and j ranges from 1 to 3. And the distance is nothing but the Euclidean distance. So it is basically x2 minus x1 ka whole square and y2 minus y1 ka whole square. So that is what we have to do, what we have to calculate effectively. So in the first case, it is 3 minus 1, 2 square plus 0 square. So the output is 2. And then in rest of the cases, I can fill it uh, accordingly. So let us just fill this. And corresponding to that, we have to take the decision. Decision of centroid. And how we'll take decision, I will just show you. And then for C3, the uh, distance is 8.1. Now we have to comment that whether point 1 is belonging to cluster 1, cluster 2, or cluster 3. And we have got the distance from point 1 to each of these clusters. Now, how we can take decision whether whether point 1 belongs to any of these clusters? So we have to check that whichever distance that we have calculated, whichever is minimum, so we can say that P1 belongs to that particular cluster. So in this particular case, we can see P1 is P1 distance between P1 and C1 is 2, and which is less than in from any other cases. So therefore, P1 can be considered in the group of C1. So the cluster is C1. Then in the next case, now let us calculate for P2. So if we take the distance again, so it is 5.1, 7.3. And over here as well, you can see that again P2 C1 distance is lower than any of the cases. So therefore, decision should be in favor of cluster 1. Then the next one for P3, the distance from C1 is 5.3, 2.2, 5.7. So in this case, now you can see that P3 C2 has the lowest distance amongst all. So therefore, uh, decision would be in the form of uh, cluster 2. So in the next case, it is 5.4, 5.4, 5.1. So in this case, you can see that 5 point is the lowest one among these two. So therefore, it would be C3. For P5, it is 6, then 2, then 7.9. So in this case, it would be C2. Then for P6, it is 8.1, then 7, then 3.2. So therefore, again, it would be C3. Then we have P7, which is 0, 4, and 6.1. So obviously, because we are calculating the distance from P7 to uh, P, we are calculating distance from P7 to P7 itself. So therefore, the value is 0 because our initial guess of this centroid is C1 is to be zero point 0.7. So therefore, the decision would be in favor of cluster 1. Fine. And again, P9 to P9 distance is, sorry, P9 is, so over here P8's distance would be 6.1, right? Then we have 6.7 and then 0. So we can see that P8 again, they have been given that P8 is also a cluster. So therefore, belongs to C3. And then we have 3,7. So again, it should be 0. Rest of the cases uh, we can leave because anyway, this would not make any changes because P9 is already the cluster. So therefore, it is C2. So now we have got the data points along with their belongingness of the corresponding clusters. So now let us assimilate all the cluster 1 data points. So if I assimilate all the cluster 1 data points, you can see that it is basically coming P1 belongs to cluster 1, P2, then this one that is P7. That's it. For C2, C2 के लिए है P3. Then we have P4, P5, P5, P6, P7. Let me just see. I think I'm making some mistake. Yes, so C2 is P9 and C3 belongs to P4, P6 and P8. So now we have got the data clusters, and based on these data clusters, now we just have to calculate this centroid. So for that, let me just take another page and copy some of the parts from this particular page. So centroid for, so after iteration one, centroid for cluster one is equals to, so it is 1 plus P2 is 2 plus P7 is 3 divided by 3, and then the y-axis value are 3, 2, 3. So 3, 2, 3. So which is actually 2 comma 2.7. For cluster 2, it is basically 5 plus 3 plus 3 divided by 3 divided by 3. Cluster 3. So here is 8 plus 9 plus 7. So effectively this is 3.7 and 8. And over here we have 8 plus 10 plus 9 and 5 plus 7 plus 4. So this is 9 comma 5.3. So we can see that these are the new cluster centroids. So therefore, let us now just scan through the solution. So 9.53, 3.78, and 2.27. Yeah, so this is the correct answer. So in the last week also, we had seen similar problem like this. So in that particular problem, uh, we had to find the problems, we had to find the points belonging to a particular cluster. Say it was, I think, for cluster 2, we have to consider that which are the points that belongs after uh, iteration 3 or something. However, the process was ditto same because it is vanilla K means clustering only. Okay. So the next question states that what is the primary idea behind mean shift clustering? So in case of mean shift clustering, if I just show you a diagram, so how you proceed in case of a mean shift clustering method. So the first process, what you do, you choose a window with a proper bandwidth. So in this particular window, you try to find the center of the window, and then in this particular window, after finding the center, you will enclose some of the data and you try to find the mode of the data. And mode means what? Mode means where the more densely packing of the data is basically occurring, or more amount of data is present in that particular area. So that is what mode means. Now you try to see that where the mode is, and based on that, you basically try to shift the mean of the window. So over here, you started with this particular uh, uh, data boundary, and then you had the center of this particular window, and then you try to find the mode of the data that is basically enclosed by the window. So let us consider this is where the mode lies. Now what you will do, what this mean shift algorithm will do, mean shift clustering algorithm will do, it effectively shift the mean or the center of the window to this particular mode of the distribution. So here you are doing the mean shifting of the window function to the mode of the data. So from the center of the window, so you got a center, and from the center, now you are moving to the mode of the data where the data is basically densely packed. So this is effectively what mean shift clustering basically means. Now this is also an iterative process, and as because it's an iterative process, so there is and the mean that by which you are basically doing the mean shifting operation, that itself needs a mathematical background. And over there you have, for example, you first have to decide the window. Now there are several sort of window functions are there. It could be any sort of window function. Let us consider it could be a radial basis function. It could be a normal distribution function. It could be uniform distribution function. So you have arbitrary choice of these sort of distribution functions. And along with the distribution functions, as we already know that many of the distribution function is basically parameterized by some of its parameters. So for example, a normal distribution is parameterized by mu and sigma. So you have to find those parameters as well. So for parameter estimation, we know that we use Parsing window technique. So we have to apply Parsing window technique to estimate the parameters of the what you call the window function. So therefore, when you start solving estimating the parameters, you know that you have to take derivative, and from the derivative, you basically apply gradient descent rule, and then you subsequently get the convergence of the algorithm. So therefore, effectively, you shifted your mean from this point to this point. Let's say in the next iteration, what you will do, you will create a uh, another window centering around uh, this particular path. Then again, uh, you will shift your mean from this point to this point. So it will be shifted over here. And in this way, through iteration, so here I have just shown directly this point to this point, but the shifting process are quite very small such that you basically capture the data distribution very well. So this is, let's say, iteration one, this is iteration two, this is iteration three. Let's say this is after iteration 10. This blue circle is after iteration 10. And then subsequently, if you go along with another sort of iteration, so at the end, you will reach in this particular position. And there you can see that there is a cluster is present. So in this way, you do the mean shift clustering. So now let us see the options. So what is the primary idea behind mean shift clustering? So iteratively shifting the data points towards mean of the entire data set. So that is not the uh, 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 that is not the goal of mean shift clustering. Assigning data points to clusters based on predefined centroids. This is also incorrect because any of the clustering methods that you have seen, it basically starts with an initial assumption that you have certain clusters, and based on certain distance metric, you basically reassign the data point to a particular cluster group. So assigning the data points to a cluster based on predefined centroids, this is incorrect. Then minimizing the sum of squared distance within each clusters. This is also incorrect because in case of mean shift clustering, the prior target is basically to shift the mean in some sort. Minimizing the sum of the squared distance will not do anything in this particular case. So therefore, it is also an incorrect option. So the last option states that shifting data points towards the mode of the data distribution. So that is what I have already told you, that you start with a window, you calculate the center of the window, then the center means for example, in the case of a Gaussian distribution, the center could, or a normal distribution, the center could be the mean. So therefore, you have to estimate the parameter. So in this particular case, you start with a window, you try to calculate the center of the window, then based on the distribution's width or the bandwidth, or in case of normal distribution, it is basically considered as a 95% confidence interval. So within that confidence interval, whatever data you capture, you try to calculate the mode. And then you shift the from the center of the window to the data mode. So that is what it is basically. This last statement is indicating that shifting data points towards mode. And mode means what? Where the data is highly packed. So therefore highest density area. So over here you can see that here obviously mode is high because this is a highly dense, this is a densely packed part of the data. So therefore shifting data points to towards the mode of the data distribution is the correct answer. Okay. So the next question states that what is the main objective of HSC? So how HSC works? Already we have told you that let's say you have a data distribution something like this. And again, as we have already discussed that these techniques are iterative. So let me just restrict myself from going far to this. Yeah. So this particular cluster is okay. So in case of HSE method, we declare each of the point as the initial clusters. So we consider each of the point is basically a cluster. Then based on some sort of a similarity matrix or distance metric, we try to group the clusters. So we started with the individual clusters, and then what we did, we tried to club them together. And in this way, from an individual cluster, you will get a global cluster. So how you can do this? So you can check the distance between any two clusters or any two point pairs. So in case of HSC, the point pairs are nothing but the initial clusters. So in this particular case, you can see that you started with the initial clusters like this, and then you calculated the distance between these two. And you found that out of every point pair, this particular distance is the lowest one. So what you will do, you will club them together. So now effectively you have a green cluster. Then from this green cluster, so this is at iteration 1. Then what you will do at iteration 2, the illustration, in my opinion, illustration is quite important because in the next question, we'll see that a similar type of numerical example is framed based on HSC only on this particular uh, concept. Now, after iteration 1, you have absorbed these two data points in the green cluster. You had initially these two red points, which were individual clusters. Now, after iteration 1, you saw that after calculating all the distances, this particular distance is the lowest one. So you have clubbed them together in the green cluster. So now you can think that instead of having uh, the individual clusters, you have got a overall cluster which is basically illustrated in the green color. Then what you will do, you will calculate again the each of the point pair distance. And in this particular case, instead of having these two data points, you can take an average of these two data points. So which is basically the centroid of the cluster, right? Then again, we'll calculate the distance between these two, from this point to this point, this point to this point. So that means we have to again calculate dij, all possible distance, all possible distance between all the point pairs. Then let us consider you have seen that this is the smallest distance that you have over all the data points. So we'll club them together. So in this way, iteratively, you can see that you started with, let's say, let me just create the cluster with another color so that you can see that two different clusters have been now formed. So initially we started with individual clusters with red color, and now you can see that with iteration, you can see that different clusters are being made because you are clubbing them together based on some similarity matrix or distance metric. So effectively within a cluster, so let's say this is cluster one, or let's say after all these things, let's say after 100 iteration, you have got so let us consider this is the situation that you got after 100 iterations. So which is basically means that one side of the data is for the pink cluster and one side of the data is for the green cluster. This is what you get after 100 iteration. Now, in this case, you can see within a data cluster, all the data are densely packed, which which means what? This means that within the class, the data variance is low. Because let us consider you are creating a cluster like this, and let us consider you have another data like this. Let's say initially at iteration 1, you have grouped these two together. Now at iteration 2, what you will do? You have this centroid at this position, average of these two data points. Then you are calculating distance from this point to this point and this point to this point. Now obviously the variance over here is very high and the variance over here is very low. Variance means what? Variance means from the mean of the distribution how the data point is spreaded over. So you can see that spread from this centroid to this point is very high. One second. Is very high, and whereas this is very low. And as because the distance is low, what you will do in iteration 2, you will club all these three together. And you will not club this one with this particular data cluster because now the centroid is this one, and again the value is quite high. So you can understand that within a cluster, the variance of the data, the variance of data is low. And in contrary to that, let us consider you have another cluster over here, which comprises different data points. So over there also this point will be valid within. So this is within cluster case. So within cluster data variance is low. At the same time, you can observe that interclass or intercluster variance is high. So there are two terms. One is inter and another is intra. Intra means within and inter means in between two clusters. And intra means within a cluster. So over here, the situation is intra. The situation is intra. And in between these two clusters, the situation is intercluster. So over here, we can conclude that in case of intra-class cluster, the variance is low, and inter-class cluster, the variance is high. Okay, so let us now see that what are the options that they have given. Maximize the within class cluster variance. So sorry, minimize within cluster variance. So they are saying within cluster variance should be minimized. So that is fine. Maximize between cluster variance. So that is between cluster 1 and cluster 2. So between cluster. So that is intercluster. And the variance should be high. So maximize between class cluster variance. So this is also fine. Minimize number of clusters. HSE has no role in reducing the number of clusters because it's an heuristic process. So you cannot have any choice on creating smaller number of clusters because HSE has no role on that. Maximize the number of data points in each cluster. Again, you cannot have any say on that. Okay. So minimize within class cluster variance is a the complementary statement is maximize between cluster variance. So therefore, both of these answers are actually correct. If you have ticked any of them, you will get the correct. Uh, you will get the marks. Okay. When m equal to 1 in fuzzy k-means, the algorithm behaves similarly too. So in case of normal k-means clustering, or in the vanilla version of the k-means clustering, we have seen that you have a pool of data and then you start with a initial assumption that your data centroids have been given, or you in randomly initialize the data centroids through the point distribution. And then iteratively, you basically try to find that whether a data belongs to any given particular cluster or not. And based on that, you update the cluster and subsequently you run the iterations until you reach a convergence. Now, after getting convergence, when the clusters have been formed, now the decision is hard at the inference time. That with if you have already seen that your data, if your point P belongs to group cluster group, let's say 1, so the decision is hard. You cannot say that it has some sort of an uncertainty of class belongingness to group 2 or group 3 or group number n. So therefore, the normal k-means clustering method, or the standard k-means clustering method, is basically uh, sort of a strict uh, decision rule based thing. But in case of fuzzy k-means clustering, the moment you increase the m value, so what it does is it increases the uncertainty property of the belongingness of any data point to any data cluster. So there you cannot finitely say whether a point really belongs to or certainly belongs to class omega 1 or sorry cluster 1 or cluster 2 or cluster 3 like this. So it associates with a sort of a uncertainty metric which basically tells that with 70% confidence I can tell you, let's say point 1 will belong to cluster 1, and there is 30% chance that it may not belong to cluster 1 as well. So within the 30%, your choice may be towards cluster 2, cluster 3, like this. So this is what fuzzy k-means cluster basically means. Now, when m is equal to 1, so the question is, when you have m equal to 1, then how fuzzy beam clustering behaves? So the behavior is, when m equals to 1, your fuzzy mean cluster becomes a normal k-means clustering or a standard k-means clustering, because in standard k-means clustering we didn't have any uh, m operator, which basically introduced the what you call the uncertainty property. So therefore, uh, the fuzzy k-means clustering, if you put m equals to 1, so that means you have 100% chance, or the 100% probability of stating that point 1 belongs to cluster 1. So therefore, the decision is quite strict over there. So M means that there is no uncertainty. It is fully certain. So certainly you can comment that whether data point 1 belongs to a particular cluster group or not. So therefore, this is no uncertainty case. So no fuzziness, and therefore this is becomes standard k-means clustering. Again, it is not an HSE, because HSE totally works on something, uh, both HSE and mean shift clustering basically. They work on something different methodology. Okay. The next question states that in mean shift clustering, what is the kernel used for? So already in the last, yeah, in this particular slide, let me just copy this part. So this is a typical mean shift clustering looks like. So you, to begin with, you consider a window function, and that window function is basically a probability density function specifically. And then it is also parameterized by some of its parameters. For example, in case if you consider that your window function to be a normal distribution, it is parameterized by mu and sigma. So you have to estimate the mu and sigma over there by any sort of parameter estimation technique. So in this case, we might use Partial window technique. And Partial window technique already we have seen probably in week 4 or something. So that is not an issue to you. So this this window is also referred as kernel of the distribution. So, and how you basically evaluate the parameters of the distribution? Through Partial window technique. So that means this kernels basically means the uh, mm, the density function. So this kernel or window basically means the probability, the distribution function or the density functions. PDF. So, and these PDFs have different sort of shape. So it could be a Gaussian, it could be uniform, could be skewed. So there could be any sort of functionalities that you employ. And obviously, as because the equation for each of these, it could be even triangular. So obviously, as because you can see, as because you can understand that the distribution functions, because effectively you have a closed form function equation as well. As because the function representation is different, so obviously their cards will also be different. So that means this K or the kernel basically means the PDFs of different shape. So in this particular figure, I showed you a circular kernel. This is just for an illustration. But in general, you can fit a, Gaussian distribution. And if you take a top view, so for example, from top, if you see, then you will see uh, something like this. So if you see from the top view, you will see a circular shape like this, or ellipse, or it could be an ellipse as well. So therefore, now let us see that what the options are saying. It defines the number of clusters. That is not, because kernel basically means the window functions. Window function has no role on defining number of clusters. In the case of mean shift clustering, you initialize your window, you get a center of the window. So let's say in case of a Gaussian distribution, the center of the window is the mean of the window, mean of the data distribution that you can find from the Barson window technique. Then uh, the data that you are enclosing within that area of the data distribution, you capture the mode of the data, and then you shift your window from the center position of the data distribution to the mode of the data distribution, which means that from the center to the densely packed area of the data. So therefore, in mean shift clustering, what is the kernel used for? The kernel is basically used to represent the shape of the density function. So that is what we have already talked about. It specifies the dimensionality of the data. Dimensionality data is no way related with clustering, because dimensionality data you have seen in the PCA week. It has no obligation with the clustering process. It determines the number of iterations. Again, you're not, you have no say on number of iteration, because number of iteration is basically decided based on the step size and uh, the convergence relation of the gradient ascent rule. So therefore, again, it determines number of iterations. That is also incorrect. Okay. The seventh question states that what is the key difference between fuzzy k-means and traditional k-means clustering algorithm? So already we have done enough discussion on what is standard k-means distribute clustering and fuzzy k-means clustering. So let us scan through the uh, fuzzy k-means is a supervised learning algorithm, and while k-means is an unsupervised algorithm. Now, the fuzzy k-means, or be it a fuzzy k-mean or standard k-mean, these are clustering techniques. Clustering techniques are uh, themselves represent the unsupervised regime of learning. So it doesn't matter whether it is a fuzzy or it's a traditional k-means. Ultimately, it is a clustering process And clustering itself is an unsupervised learning process. So therefore, stating that fuzzy k-means is a supervised learning algorithm, that is incorrect. And if you remember, I started this live session with uh, the initial statement that we will see clustering techniques, which is a unsupervised method of learning. So therefore, fuzzy k-means cannot be a supervised algorithm. Okay. Fuzzy k-means assign each data point to exactly one cluster. Fuzzy k-means does not assign each data point to a cluster. HSE, rather, on the other hand, initially it uh, takes a notion that each of the data point it basically assigns as a cluster. But fuzzy k-means does not do this. Then you have fuzzy k-means does not require the number of clusters to be specified. Again, this is wrong because in any of the clustering method, you initially you have to start some perusal of the number of clusters. You have to take a initial guess. So but k is basically the number of clusters. So you have to start with a uh, initial assumption. So therefore it is incorrect. Then fuzzy k-mean allows each data point to belong to multiple clusters with varying degree of membership. This is what I was talking about previously as well. That in case of fuzzy k-means, the moment you introduce the M factor, the membership factor, it basically brings the uncertainty parameter to the picture. And the moment you bring uncertainty, so that means at that particular point of time, you cannot finitely say that a data point belongs to a particular data cluster uh, finitely. So therefore, there should be some sort of an uncertainty that it to the data cluster belongingness of the data point. So let us consider you put m is equals to zero point 0.7 or something. So then you can say that the data there is a 70% chance that the data may belong to this particular group. Rest of the 30% chance is there that it may not belong to uh, group 1 or group 2, something like that. So that means on this 30% uncertainty, the data point may belong to any of the other groups. So that means fuzzy k-means allows each data point to belong multiple clusters. And how you can ensure that this particular points to be facilitated? By introducing the factor M or the membership factor. So with varying degree of membership, because membership factor will allow that a data point might belong to cluster 1, cluster 2, cluster 3, because it brings the picture of uncertainty in the k-means clustering algorithm. So therefore, this is the correct answer. Okay. So the next question states that if we utilize the HSE clustering method on the given data set that have been provided below with an aim of identifying the clusters based on the smallest value obtained from the Euclidean distance. So you have to focus on this particular line, that HSE method you have to utilize on the given below data. Aim of identifying clusters based on smallest value obtained from the Euclidean distance calculation. So they have mentioned that what should be the distance metric. It is minimum of the Euclidean distance calculation. So this is basically the rule that they have provided. Instead of giving this particular rule, if they have stated something else, you have to abide by that particular rule, or you have to follow that particular rule for making the certain decisions for clustering process. And over here you have a total of 6 data points, and the coordinates have also been given over here. And this particular matrix is basically mentioning the distance matrix of 6 points. So that means P1 से P1 का distance कितना है? So obviously it should be 0. Then P1 से P2 का distance कितना है? P1 से P3 का distance कितना है? Likewise. So based on this information, we have to create the dendrogram. And we know that in case of HSE algorithm, we basically end up with a dendrogram representation, and that is what basically asked to derive. So at iteration 1, we can start. At iteration 1, we have to find the smallest value of Euclidean distance, but do not consider these 0 points, because these 0 points have came into the matrix because of this particular operation. You are calculating distance of P1 from P1 itself. That means you have a point P1 and you are calculating distance.
Sir, can't hear your voice.
Sir, you are not audible, sir.
Yeah. So now we have to find. So as I was saying that you got this distance matrix, which is basically the tabular representation of the Euclidean distance calculated from each of the point pairs. Then the on diagonal elements are basically the distance from the point to itself only. So therefore, effectively, you will get 0. So now you have to find the minimum value in this particular distance matrix, excluding the 0 values, which is basically coming in the on diagonal positions. Because effectively, you are calculating the distance of P2 to P2 itself, which has no physical meaning. So among the whole distance representation, we can see that P3, P6 distance is the lowest one, 0.1100. 0.1100 is the lowest value in the matrix. So again, P6 to P3. So this is uh, yeah. So this is the lowest value inside this particular matrix. So after first iteration, we got the uh, first cluster of data pair is P3, P6, right? Because as distance between P3, P6 is lowest in table 1. Sorry, table 2. This is table 1, this is table 2. So this is the first cluster. So we can call P3, P6 as cluster 1. Now we have to go for iteration 2. So how iteration in iteration 2, we have to calculate this distance matrix. And what are the changes that you will observe? That is the main point. So P1, P1, these 2 points will this point will be there. Then you will have P2. Fine. P P3 you will not have, because now you can see that you had P3 and P6. As because the distance was very small in between these two, you have clubbed them together. So you will not get P3 and P6 individually, because now they have been clubbed together. That is the first striking point that you should keep in mind. So over here you had P1, P2, P3 you will not have. Similarly, P6 also you will not have. So I can write P4, I can write P5. So similarly over here P4, P5, and then I can write C1. And C1 means what? This is P3, P6. Okay, fine. Now let us again fill the values. This is a tedious process. So P1, P1 के बीच में it would be 0, P2, P2 के बीच में it would be 0, 0, 0. So all the on diagonal elements will be 0. Now we have to write the off diagonal elements. So already for some of the cases I already have been given with the off diagonal elements, that is 0.2357. Then P4, P1 to P4 is 0.3688. Then you have 0.3421. P2 से P1 के बीच में distance is 0. Let me just write only two digits, 0.23. Or will it make any confusion? We have 235. Let me write 235. Okay, so P2 से P4 का distance है 0. 2042. Then we have 0.1388. 1388. P4 से P1 का डिस्टेंस है 0.3688. Then we have 0.2042 and P4 से P5 का डिस्टेंस है 0.2932. Then you have P5 to P1. So that is 0.3421. Then you have P5 to P2, 0.1388, 0. That is P5 to P4, 0.2932. Yeah. So now we have filled this part. Now the question is, how can we calculate the distance of P1 to C1? That is the catch now. So distance from cluster to point. So in our case, let's say distance from cluster 1 to P1, they have already mentioned that identifying clusters based on smallest value of the Euclidean distance. So that means we have to calculate minimum of cluster 1 में कौन सा data है? We have P3 and P6. So individually we have to calculate P3 से P1 का distance क्या है and P6 से P1 का distance क्या है. And then we have to take the minimum. Right? And already it have been provided. P3 से P1 का distance is 0.2218 and P6 से P1 का distance is 0.2347. So it is minimum. So therefore I can write 0.2218. Right? So I'm filling up this part. So 0.2218 and over here also 0.
Sir, excuse me, sir.
Yes.
Sir, can you repeat this distance calculation alone, sir? D of C comma P.
Okay. Yes.
Yes. Thank you, sir.
Okay. So the point is only finding the distance between the point pairs, that was fine because it is just a Euclidean distance root over x1 square minus x2 square and y2 square y2 minus y1 ka square. So this is what the normal Euclidean distance means in between any two point pairs. Now the question is, the moment you incorporate some of the points inside a cluster. Now the question is how to calculate the distance between the clusters to point pairs. That means C to P. Now for that, the method to calculate the distance is basically is C1 में let's say in the C1 you have two data points, that is P3 and P6, and you want to calculate the distance between C1 to P1. So individually you have to calculate इस C1 के अंदर जितने भी डेटा पॉइंट्स है उनके उनके बीच में डिस्टेंस क्या है. सो दैट मींस डी C1 P1. अब C1 किन किन डेटा पॉइंट्स को लेकर बना है. सो दैट इज P3 P6. So they calculate the distance between P1 to P3 as well as P6 to P1. So that means the distance, and then I have to consider the minimum distance among these two. So it is minimum of distance P1 से P3 का distance क्या है. So that means P3 P1 P1 to P6. Similarly, let's say if I have to calculate D C1 P2, So C1 is basically constituted with P3 and P6, and I have to calculate the distance between C1 to P2. So that means individually I have to calculate the distance between P2 to P3 and P2 to P6. And then I have to consider the minimum value. Because they have said already that the smallest value of the Euclidean distance. So minimum of D P3 to P2, comma D P6 to P2. So the main fundamental thing is see whatever cluster we have within that cluster. If you have n number of data points, you have to calculate the distance from those n number of data points to the point concerned, and then you have to take the minimum value. So that is how you have to calculate the distance from cluster to point. Inside a cluster, if you have n number of data points, then from all the n number of data points, you have to calculate the distance of the point concerned. So in this case, that is P2. Then you will get individual distance like this, and then you have to take minimum so that you can get the uh, distance between cluster to point. So in this case, dp3p2, so dp3p2, p3 से p2 का distance is 0.1483 and p2 से p6 का distance is 0.2540. So that means it would be 0.1483. So it is 0.1483. 0.1483. Then by the same logic, we have to calculate the distance. So that is, we have to calculate distance C1, comma P4. So which means you have to calculate D. Sorry, you have to write minimum of the individual distance from P4 to each of the points inside C1. So therefore I can write D P3, comma P4 and D P6, comma P4. Because cluster is basically made up of P3 and P6. So P3 से P4 का distance is 0.1513 and P4 से P6 का distance is 0.2216. So again it would be 0.1513. So I can write 0.1513. 0.1513. Then we are left with the last case, that is P5 से C1 का distance क्या है. So I hope you got the point. So P5 से P3 का distance is 0.2843 and P5 से P6 का distance है 0.3921. So therefore 0.2843 is the lowest one. So I can write 0.2843 and 0.2843. So now I have completed the distance matrix, which I can annotate as table number 3. Now again you have to check. Check minimum value in this table T3. So what is the minimum value in the table 3? So let us now scan 0.2357, 0.3, 0.3, 0.22. So this could be the lowest one. 23, 20, 13. Okay, we have got 13. 14 is also high. 36, 20, 29, 15. 3413 2932 2828 15 14. So we can see that this is the lowest value that you can receive in table number 3. So therefore you can see that point P2 to point P5, the distance is lowest in table 3. So the lowest value is 0.1388, which corresponds to D P2 to P5. So if I just start drawing the dendrogram, so let's say you have the data assimilated like this. First you got 3 and 6, then you got 2 and 5. Which basically create a whole cluster group. And then along with the, I mean, in this particular way, in each iteration, you have to calculate this particular matrix. And then you have to proceed with the next one. So this is the way you will actually reach the solution. But so far as the exam point of view is concerned, uh, even in the live session of MK Bhuyan sir also, he has mentioned that the exam question will be even easier than this one, because you can understand that for each of the iteration, you have to calculate this whole matrix again. Then you have to find the minimum, and then you have to proceed again. So therefore, it is quite a laborious job. So far as the final exam is concerned, you can understand that uh, there is high possibility that you will not see something like this sort of question. But for the completeness, let me just do another step. So let's say iteration 3. So in iteration 3, so again, let us construct the table. So P1, P1. So we already have seen P3 and P6 is creating a data cluster. P2, P5 is creating a data cluster. So I can write P1, P4. Then I can write P2, P5 and P3, P6. Because I cannot write them as an individual, because now they are the part of they're the part of the clusters. So therefore I can write P2, P5 and P3, P6, right? Sorry. So P1 के बीच में distance तो 0 होगा, सारे on diagonal elements will be 0. Now let us try to see that what would be the other cases. Now P1 से लेके P4 तक का distance is 0.3688. 0.3688. Okay, so here would be also 0.3688. Okay, now we have to calculate the distance between this is, let's say this is your cluster 1, this was your cluster 1, this is your cluster 2. So effectively I can write cluster 2 over here and this is cluster 1. So as over here also, this is cluster 2, this is cluster 1. Already we have seen how to calculate the distance between clusters and points. So C2 से लेके P1 तक का मेरे को distance calculate करना है. So for that what I will do, I will calculate the individual distance between the points that is residing inside the cluster to the point concerned. So therefore I can write minimum of D P2 P1 comma D P5 P1, right? So P2 से लेके P1 तक का distance क्या है? So P2 P1 distance is 2357, or P5 P1 distance is 0.3421, right? So I can write P2 से लेके P5 वाला 0.2357. Okay. So in the last case we had calculated P3 से लेके C1 का distance था 0.2218. So it is 0.2218. So I can write over here 0.2218 because this is a symmetric matrix. So I can write it in this fashion as well. So it is 0.2357. Fine. Then we have to calculate P4 से लेके C1 का distance. So in the previous page we have already done this. P4 से लेके C1 का distance is 0.1513. So this is 0.1513, right? So I can write 0.1513, and then we have over here P4 से लेके C2 का डिस्टेंस हम लोगों को कैलकुलेट करना पड़ेगा. So D of C2 P4. So D of C2 P4, how we can calculate? Again, minimum of D P2 P4 and D P5 P4, right? So in this case, you can see that P2 से लेके P4 का distance is basically 0.2042, and P5 से लेके P4 का distance is 0.2932. So the answer would be 0.2042, and over here also 0.2042. Okay. Now in this case, here the problem is you have to calculate the distance between clusters, right? So that means you have to calculate distance between C2 to C1. So if I just expand this particular thing, C2 means what? P2 P5, and C1 means what? P3 P6, right? Minimum of this thing, minimum of. So that means now you have to calculate distance between this to this, and this to this. So you'll have 4 cases. And out of all these 4 cases, you have to see that whichever is yielding the lowest value. So if I just write it P2 P3, then P2 P6, then P5 P3, and P5 P6. Now out of all these, whichever is the lowest one, P2 से लेके P2 से P3 is 1483, right? Then we have P2 से लेके P6, that is 2540. Anyway, ये नहीं आएगा because 2540 is a high value than 1483. Then we have P5 से लेके P3. So P5 से लेके P3, that is 2843. Again, this is a high value. You can discard this. And P5 से लेके P6. So P5 से P6. Again, 0.3921. This is also a high value. So therefore, among all these cases, we can see that 1483 is the lowest one. So I can easily write that is 1483, 0.1483. So in this particular case, now we have to find that what is the smallest value in the whole matrix. So this is 3 6 2 3 2 2 3 6 2 3 2 2 2 0 2 0. So this one is the lowest value. So I can write in this particular case that C2 से लेके C1 तक, मतलब C2 C1 is creating another cluster. So that means in the earlier case we have drawn that 3 और 6 बना रहा था cluster, 2 और 5 भी cluster बना रहा था, and in this case we have seen that these two are clubbed together. C2 C1 भी club हो गया है, right? Now if I further do this, because in general nobody asks these sort of questions, because this is very tedious to do. I don't know why they are giving these sort of questions. So P1 से लेके now let me just again write. We have C1 that is comprising P3 P6, then we have C2 which is P2 P5, then we have C3 which is a joint cluster of C1 and C2, right? Now how can we create the matrix in this particular case? So sorry, this P1, this P4. Now what will happen? That is the catch. So in this particular case, you can see in the earlier case, you had two distinct clusters, C1 and C2. So that is why you are putting C1 and C2 individually in the table. Now you can see that you had the individual clusters that now have been grouped together as C3, right? So that means there is no point of writing C1 and C2 individually, because after iteration 3, you have clubbed them together. So you will write C1, C2 together. So C1, C2, or directly you can write C3 also. Whichever nomenclature you want to write, you can write. Now P1 से लेके P1 का distance, all the on diagonal elements will be 0, and we have to think about the off diagonal elements. So for the so far as the off diagonal element is concerned, I can write that P1 से लेके P4 का distance is 0.3688. So 0.3688. Now you have to calculate P4 से लेके C1, P4 से लेके C3 का distance. C3 itself comes with C1, C2. So that means now your C3 is P2, P5, P3, P6. Now you have to calculate distance from P4 to C3, which is basically distance of, sorry, is minimum of, every time I'm writing the same thing, minimum of D P4 C1 D P4 C2. Okay. Now let us see whether we have the values or not. C2 से P4 का वैल्यू, P2 P4 we have and C1 P4 also. I'm myself confused now. Yeah, yeah. So just follow this one. Yeah. So we have to calculate P4 से C1 का distance. So see P4 इस मैट्रिक्स में है, यहाँ पे P4 है, P4 से C1 का डिस्टेंस. So this was C1 का डिस्टेंस 0.1513. So therefore I can write minimum of 0.1513 and P4 से C2 का डिस्टेंस कितना है? P4 से C2 का डिस्टेंस is this one 0.2042. 0.2042. So therefore it is what? It is 0.1513, and over here also it is 0.1513. Now we have to calculate this distance D P1 से लेकर C3. So that means minimum of D P1 C1 D P1 C2. Charge to okay. So I can write D P1 से लेके C1 का डिस्टेंस इज 0.2218 0.2357. So obviously it would be 0.2218. So this is 0.2218 0.2218. So now let us see what is the condition. तो सबसे कम वैल्यू है P4 से C3 का, right? So we can again draw the figure. So we had 3 6, we had 2 5. This is at iteration 1, this is at iteration 2. At iteration 3 we had a connection between these two clusters. This is C1, this is C2, this is C3, and now we are also attaching C3 with point 4. So this is at iteration 4. So we can call it as C4. Fine. And after this, we have your C4 is C3 P4. So now you can see that you have covered P3, P4, P2, P5, P6. Only P1 is left. और कोई iteration करने का जरूरत ही नहीं है. You can directly connect this one. So this is the correct answer. This is a quite a bit of task to complete. Okay, so let us now move to the next question. How does hierarchical HSE work? Again, the same type of question they have given. It randomly assigns data point to different clusters and then iteratively adjust the assignment until the stopping criteria meets. This is incorrect. It start with each data point. Yeah. So HSE already we have told that it first does initialize the process with a notion that each of the data point is itself a cluster. So this is correct. And then iteratively merge the closest pairs of the clusters until the stopping criteria reached. So that is what we have done. So over here also, we considered that initially all the data points are even itself a cluster. Then we have merged the data points. So for example, 3 to 6 we have merged, then 2 to 5 we have merged based on the some distant criteria. And what is the criteria that is given over here? And till when we have till what point we did the same? So this is iteration 4. So we did the same till we reach the last data point. So that is the stopping criteria. So after you cover the all data point, then you can stop the process. So therefore, uh, this is the correct answer. Okay. And the last option, last question states that what parameter in fuzzy k-mean controls the fuzziness? Already we have seen the membership parameter, because the membership parameter basically introduces the uncertainty metric, which basically leads you to the fuzziness of the fuzziness of the k-means problem. Because in sort of traditional k-means problem, the decision rule is quite strict. You can have either no state or yes state, and in the fuzzy k-mean state, fuzzy k-mean clustering method, you can actually uh, say that there is an uncertainty that your point P1 might belong to any other data clusters as well. So therefore, the membership parameter basically brings the fuzziness or the uncertainty issue in the clustering process. Week 10 annotated. Yeah, so this is the answer for the diagram that we had solved till this point. That 3 6 was a cluster, then 2 5 was a cluster, then 4 is attached with this one. And as because you are left with point 1, so there is no point of doing that matrix calculation again. So you can directly connect this thing with the last cluster. Let me just upload these slides. Okay, so anyway, I'm running out of the battery, and over here it's raining, so we don't have electricity as well. So I think now we can end the session. So thank you for joining.